So 1-3 is the basic properties of real numbers. Real numbers. So we're not talking about imaginary numbers here, right? Now we're talking about real numbers still. So let's start with this first part. So we have some properties of equality. And you might be saying, yeah, of course A equals A. Like, I know that already. A is the same thing as A. 1 equals 1, 2 equals 2. Why do I care? In geometry next year, you will do a good amount of proofs, statement reason proofs, where you have to, God bless you, prove shapes congruent or similar. And you will utilize what's called the reflexive property. If you have, say, a triangle like this that shares a length, and you're trying to prove triangle 1 equal to triangle 2, well, segment AB is the same in both triangles, so you would use what's called the reflexive property. Meaning AB is the same in both triangles because it's shared, it's adjacent, it's the wall between these two rooms. That's where reflexive will come into play. Symmetric makes sense. Symmetric is just saying if A equals B, B equals A. Right? I could switch the order in which I make that statement there. Transitive, when I think of transitive, I think of the chain rule. The chain rule. So, if, let's say, I'm looking around the room, let's say Bridget and Altea, how am I saying it? Am I right? Altea. Bridget, Altea, and Sean? Yes. Bridget, Altea, and Sean are all the same height. So you could say, Bridget is equal to the same height as Altea. Altea is equal to the same height as Sean. Therefore, Bridget equals the same height as Sean. Does that make sense? A equals B, but B equals C, so A must equal C. The chain rule of equality. Next is the additive property of equality, which simply says, if I've got a number, 7, right? 7, and I add 2 to it. And I have another number, 7, and I add 2 to it. Aren't they both going to be 9? Sure. So if A and B are the same value, and you add C to both sides, it's still going to be the same value. Additive property of equality, solving equations. And then finally, multiplicative property of equality. The same thing as the additive, instead you multiply instead of adding. So if A and B are the same, then A times C equals B times C. Again, terms that you should kind of know, vocabulary that's important. After geometry, unless you study theoretical math, you probably won't use so much of it though. Okay, but it is useful for geometry next year, so that's why I'm really hounding you on it here, so you know these phrases. Okay, multiplicative property of equality, additive property of equality, transitive property of equality, symmetric property of equality, reflexive property of equality. Each of those are named as you hear them. Commutative law. These are called field properties. There are 2 commutative laws you know of. There is the commutative law of addition and the commutative law of multiplication. What about subtraction and division? Tell me, why isn't subtraction commutative? Sean?
Because if you switch the order around, you will receive a different value. For example, 3 minus 1 is 2, but 1 minus 3 is negative 2.
Well done. Well stated too. You receive actually the opposite value, right? Always. If I do A minus B, but you do B minus A, we'll get opposite answers. So fun fact, this is one that most students never pick up on. If you're simplifying something, right? Let's say I have an equation or an expression, I should say for now, and I had the following. I could cross the whole thing off and just write what?
1.
Careful.
0.
No. Close. Negative 1. The opposites, right? So if I have a number for x and y, and I do, like we just said, 3 minus 1, well this is then 1 minus 3, right? So it's always going to become some number over its opposite whenever this is the case. So whenever you see x minus y over y minus x, it always cancels out and you put negative 1 in its place.
Is that first?
This is still commutative I was talking about, yeah. But I'm just writing a little extra rule down here. It's always equal to negative 1 when you use the commutative law improperly for subtraction. You know what I mean?
Yeah.
You can't switch the order of subtraction. It actually isn't the same. So commutative holds true for addition and multiplication only. Associative also holds true for those operations. How do you remember commutative versus associative? Well, for me, I remember when I was your age, that associative is who you associate with. And that's like your group of friends, right? And look, associative is changing the grouping. You're physically changing the parentheses spots, which changes the grouping that occurs here. So associative, associated with friends, you're grouping. Inverse operations, inverse here. If I add the opposite of a number to itself, I will always yield 0. I will always yield 0. Now with multiplication though, if I multiply a number by its reciprocal, I will always yield the number 1. The number 1. Things that you, I think, really do know by now, right? You know? Stuff that's not going to be new to you. When you add 3 and negative 3, you get 0. When you multiply 3 and 1/3, you get 1. Stuff that you should have seen in your earlier course. Identity is something that could be new for some people, but it's really self-explanatory. If I'm 7 and I add 0 to 7, I'm still 7. I'm identical to what I started with. If I'm 8 and I multiply it by 1, I'm still 8. I'm identical to what I started with. So the identity property has to do with the identity elements 0 and 1. 0 is the identity element for addition. And 1 is the identity element for multiplication. The last one is one that is probably the one that you would utilize most often out of all of these in an algebra-based course, and that's the distributive property. The word is self-explanatory. You distribute the front scalar, or whatever this is, constant, to the 2 or 3 or 4 or 5 inner terms. So in this case, again, I take A and I multiply it by B. I take A, I multiply it by C, and I add those quantities together, and I get AB plus AC. Questions on field properties? On field properties. Should be a lot of review. Okay, if you're like, man, this really is review style, I apologize. I'm just trying to get everybody on the same page. All right, simplify, simplify, simplify. Go ahead and do it yourself. It's like that first. I'm sure it's yeah. Now, you didn't have to do this, but this is what you should be thinking right here. You didn't have to write that, but that's what you should be thinking, right? Associative law of multiplication tells me I can change the order of the grouping. A commutative tells me I can change the order physically of the way they're multiplying. So I changed the grouping in this case. I grouped my numbers together, 14 times 5, so I can worry about that. By the way, quick mental math. 14 times 5. If you don't know the answer, how do you do it? If you don't know the answer off the top of your head, there is a quick way to multiply big numbers. Yes, you can do it along with multiplying in your head. There's a quicker way.
Isn't it like 10 times 5 and 4 times 5?
Yeah, you break it into pieces, right? If you see that trick, if you haven't seen it, just know. If you want to do 14 times 3, 10 times 3, and 4 times 3. 10 times 3 is 30. 4 times 3 is 12. That gives you 42. And then 42 times 5 is 210. So this answer becomes 210 xy squared w to the 4th. Give me 1 minute. I want to see something.
Wait, don't you organize it in alphabetical order though?
That does not matter at all. You know what you order it in? Honestly, the order you should really do is decreasing exponent. We're going to talk about that in this course. So if I were to properly write it, it would be 210 w to the 4th x y squared x. But it does not have to be alphabetical.
Increasing exponent.
Like this is increasing here. I'm saying traditionally you write your polynomials in terms of decreasing exponent. This is not a polynomial, so it doesn't matter. But if I had like x to the 5th plus x squared plus x to the 4th, that's not in the right order. It should be higher to lower, but only for polynomials. For monomials like this, it does not matter at all. Okay? So listen carefully. You are going to do, we were talking about naming the types of steps in the simplification that are occurring here. And this is not something that is going to be hounded on you for the next coming years, but again, like in geometry I was talking about, you're going to have to give evidence for your statements. So that's what this is teaching you about. Okay, so from where we start in the beginning, right, from here to part A, What allowed us to do that? What rule, what law, what theory, what was it, Gus?
Distributed.
Distributive, right? Take the 2, take the 2 and distribute it to both of these, and this gives us the next line, so we say that the distributive law. How about from line A to line B? What allows me to go from line A to line B? This one's a little bit weird, Olivia? What is it? Identity, very good. I'm allowed to just put a 1 in front of something and it's still the same thing. It is identical. From B to C, what law allows me to change my parentheses? Associative. Associative is about moving your parentheses with addition. So again, from B to C, it was the associative. How about from C to D? It's a little weird, that one. I'll accept multiple answers for this.
Distributed property.
Good. It's like the undistributive though, right? It's like the reverse of distributive. Look at C to D, please. From line C to line D, what we did there technically was undistributive. AKA what? What's the other word for that? We take a variable out of all the terms. You did it in your summer packet a million times. Factoring. So I mean the word we use is factoring, but it really is technically the distributive property that allows me to factor stuff out. Okay, factoring things out comes from the distributive property. And then finally from D to E. From D to E, what do you think? That one's one that's like almost too obvious that you kind of don't even see it. Not one of the ones you really learn earlier on in your career. Yeah, it's pretty much simplification, but what was the one thing we talked about where you could take a value and replace it with a value that's equivalent to it?
Commutative property?
Not commutative, that's changing the order in which they are added.
Substitution.
Substitution principle. Okay? From D to E, yes, it is definitely, PEMDAS and just evaluation, but technically speaking, this is substitution principle. So an example of this you're going to see in your homework where you're going to have to give evidence for each step along the line of the simplification. I want you to see one of these examples. I think I give you 1 or 2 of these for the homework for this section. Oh no. So this last thing we're going to talk about for 1-3 and then we're going to move on is called closure. Okay, closure. In terms of math, closure. Closure has to do with a set of numbers that is what we call closed in a system, in a specific operation. So for example, let's take a look at this one. For example here, we're going to determine whether this set is closed under these operations of addition, multiplication, and division. So, God bless you. Thank you. So what this means is this. If I look at all the numbers in this set, what numbers am I talking about? 3, 6, 9, dot, dot, dot. I'm talking about all the very good. Multiples of 3. So that's ought to be in my set. So this set S is called the multiples of 3. Are the multiples of 3 closed under addition? Meaning, if I take any of those things and add them to any of those elements of the set and add them together, do I get another element in the set?
Yes.
Yes, absolutely, right? Give me an example.
6 plus 21 is 27.
And 27 is a multiple of 3. And think about it logically. If you're adding multiples of 3, you'll always get an answer that's also a multiple of 3. And the only way to prove it's not true is to find one counter proof. If you can find one that doesn't work, then it is not closed. Is that clear? One false statement means that it is not closed under addition. In this case, it is closed. And we could try many, many examples, but they're all going to work. And the way you can prove that is by actually factoring. So try adding anything. If I add 9 plus 45, well, 9 is really 3 times 3. 45 is 9 times 3. I could factor out a 3, which leaves me with 3 plus 9, which is really 3 times 12. So in the end, if I ever add 2 things that are multiples of 3, by showing the factoring, they're always going to be multiples of 3. 3 times 12 is also a multiple of 3. So in higher level math, you're going to do this with all variables. You would call this n, and then you would say like 3n, or you would use a factor in front of it with variables instead of numbers and prove it. But I'm just using numbers for today. How about multiplication? Closed or not under multiplication?
It works.
So it is closed. Then
Yes. Yeah.
Okay. Do you agree? Do you disagree? Does anybody disagree? Is there a counter argument for that? Is there anything that you can multiply in this set by another element that does not end up in the set. You're right. Can we prove that real quick to show? Sure. Pick any two numbers again. Let's try 6 times 12. How do I know that the answer is going to be a multiple of 3? We'll just factor it again. This is 3 times 2. This is 4 times 3. So it's really 3 times 2 times 2 times 2 times 3. To be a factor, to be a multiple of 3, only one thing has to be 3. So as soon as I see what I can factor out of 3 here, whatever this is, the answer is going to be a multiple of 3. It doesn't matter what this number is. This number can be, except for the 0. This can be 1, 2, 3, 4. Any integer will make this a multiple of 3. So yes, anything that we multiply as a multiple of 3 will remain a multiple of 3. So these two are closed. Division. Is division closed?
Yes.
Yes. Where are we at? Who said it? Give me an example.
Even if you do 9 divided by 6, you'll get 1.5. 3 times 1/2 is 1.5.
But be careful. Multiples mean you can only multiply by integers, not fractions.
Oh, which means it would not be gross.
Yeah. So be careful with that statement. You guys see what he said there? It made sense what you're getting at. So unfortunately, if it's a multiple of 3, you can't have multiples of 3 that are multiples by fractions. Okay? So like if you did 3 divided by 9, you get 1/3. Is 1/3 in the set? Do you see 1/3 anywhere? Are we going to get 1/3? No. We're not going to get 1/3. These are the integer multiples of 3 in this set. So it is not closed under division because of the one thing we can show. So again, just do like 3 divided by 6. That's 1/2, right? That becomes 1/2. That is not in the set of answers 1/2. So it's closed under addition and multiplication, but not division. All right, that's lesson. So over the weekend, you're going to do lesson 1-3. Now, notice what I do in the homework. I didn't point this out last class because you're going to start picking up on it over time. I always give you homework in the section that we're working on, but I always give you a little bit of review also. When you submit your homework, submit this as one document and call it 1-3. Even though 1-2 is in there, you follow what I mean? So when you submit this homework over the weekend, call it homework 1-3. But you're still going to put the 1-2 review problems, those 3 problems for review, in the same document. So later in the year, when you're on section 5-7, I'm going to have you do a review from section 1-2 or 2-5. I always do that so you go back and do all the homework. So when it comes to the midterm and the final, we're not suddenly like, oh my gosh, where did all this come from? I haven't done this in a long time. So every night you do your homework, you do a little bit of review as well. But make it one document, please.